Yeah, thanks, Brittany. I'm Eugene, and I'm going to talk to you about how we scale at Intercom, how we scale the database specifically. I'm a staff product engineer at Intercom. It's going to become apparent during this talk. I'm not a DBA. I'm not a database scaling MySQL person. I usually work at the application layer, and it is my job at Intercom is basically to make sure the production application is healthy and available, and sometimes that does mean dealing with the database, solving problems there. So yeah, I'm going to talk through over the time some of the changes we've made and fixes we've made. But first, before I get into the details, 2 million database requests per second. Where do those come from? Why do we run so many queries? If you don't know anything about Intercom, there is a demo coming up soon. You can learn all about it. The very short version is that we're a customer service platform. So we sell a product to businesses they use to help their customers. And whenever one of those customers uses the business's application, they're sending a request to us to get data about that user. So we don't just scale with the businesses that we sell Intercom to, like we scale with all of their user bases combined. So as our customers get bigger, get more users, all those requests come to us. So that's how we ended up at such a high scale. A little bit about our application as well. It's a 14-year-old company. We started using Rails on day one and still are in the same application. 2.5 million lines of code with over 250 engineers actively working on it. Like I said, my job is to sort of make that work and scale. We have 200,000 requests between web and background jobs. That's what's driving those 2 million database requests. And we have over 1,000 different database tables powering the product. It's a very wide product, lots of features. And those tables are split across 13 different databases. It's kind of like a zoo of database, quite messy. So I wanted to give you a visual here, and I thought I'd ask ChatGPT to do it. It mostly, I mean, it looks okay. It doesn't actually have 13 databases. There's some issues with counting things, but you get the idea. So there's many databases. Some are really big. Some are hundreds of database instances, hundreds of shards. Some are very small with just a handful of tables and not sharded. So yeah, quite diverse. And you know, if you came to me and were like, oh, I'm starting a startup, can you help me design my database schema so that I can scale it in future? Like, I wouldn't necessarily draw this out for you. But like all good production applications, you know, we didn't sit in a room and design this from scratch. We had an application, we had a problem, we solved that, and we kind of iterated to a point where it works for the scale that we're at. So yeah, I'm going to kind of go through chronologically through some of those challenges that we faced. We're going to start in 2013. There's two reasons for this. Intercom was founded in 2011, so there was 2 years of history here. But like an early startup is not very interesting from a database point of view. You have a database and you put data in there and it works, and it's not very interesting. So the other reason is I started working at Intercom in 2013, so I can talk, you know, authoritatively about what happened from this point onwards. Intercom is hosted in AWS, so we use their AWS RDS service to host our database. That worked fine. At the point when I joined, Intercom was growing quite fast, so we had a reasonably large database. It was working okay, but we could tell that we were going to run out of headroom. We needed to scale up the database before there was like some issues there. So yeah, we're going to talk about a few patterns of scaling here. This first one here is vertical scaling, fancy name, just get a bigger database basically. And not long after I joined, I overheard a conversation about scaling up the database. I heard we were going to do this, and one of our engineers was talking to our VP of engineering at the time, Dara, and saying basically, okay, we pay this much for the database now, we're kind of running out of room. If we double the amount we pay, we can have a database that's twice as big. We'll let us scale for 8 months, 12 months, something like that. And Dara was like, yeah, that sounds good, but what if we paid 4 times as much money and we had a really big database, and then we wouldn't have to worry for 18 months or something like that? And you know, I was new, I was just kind of listening in, it wasn't my project, I didn't say anything, but I thought this was actually kind of crazy. I didn't know why we would voluntarily pay more money. The database we had was working, we just wanted it to be bigger. That's okay, that makes sense, but why would we make it over 4 times the capacity we need? Surely we can just scale up again later when we need to do that. But like I said, I was new, I just sort of let them do their thing, and they scaled up that database to 4 times as large as it was. And actually, in retrospect, I was completely wrong, and I'm glad I held my tongue, because I would have made a fool of myself, because I had come from a smaller company that wasn't really growing, like wasn't a startup, it was a stable business. So there it was important to size things correctly and save money. But Intercom was growing fast. So I said, oh, we'll just scale up a second time when we need to. It's easy to say that, but Scaling up, requires generally your application to stop working for some period of time. You stop sending queries to the old database, you let the new database catch up and become consistent, and then you turn the database or turn the application back on, point it at the new database. If your app's not going to work for a while, your customers are going to notice, and you probably want to tell them, and then you have to pick a window when you're going to do that. Maybe you do it at the weekend to not annoy customers. Now you have engineers working the weekend. Also, this assumes that it works well. What if it doesn't work? You might have to roll back. You might have to restore from a backup. You might be saying, oh, well, there are 4 minutes of writes that are not there because they were in the back. Well, there's all sorts of risk. The worst case scenarios are quite bad. And choosing to do that twice to save some amount of money just doesn't make sense when you will hit that 4 times eventually, right? You're just going to spend a little bit more. So luckily I didn't speak up and let Dara do his thing, and it made sense. So that's what we did in 2013. Like I said, I was new, I wasn't involved, but that was the first database scaling thing I was aware of at Intercom. That worked for a while, obviously, like we planned. We got a load of headroom. We get to stop thinking about the database, do other more important, more interesting things. But eventually, something else obviously always does come along. So we're skipping forward to 2014. Don't worry, the database is fine now. Like we said, we scaled up plenty. We have plenty of headroom. But we have a slightly different issue now, or a different challenge. So there's a new feature being developed at Intercom. It's called events. Basically, it's attaching metadata to users defined by our customers. It can be anything, arbitrary key values, and they want to be able to send events over and over and aggregate them and count them and attach them and filter on them and all sorts of features. And we noticed that it was actually all of the larger customers that are going to be our largest customers when they sign up that need this events feature. So we were a little worried that, okay, the most data intensive thing we've ever done for our largest customers could become very quickly the largest volume data in the database. And we don't want to use up all that lovely runway that we built ourselves just with this data. So we have the idea of making a new database. Instead of vertically scaling, we're going to vertically shard, meaning a second database to put that new data in. So in case you need a diagram, we have a big existing database, and now we have a little database beside it. The big database has, I think 100 tables, 106 tables at this point, and they have plenty of data in it. The small database has 3 tables and they're empty, so obviously it's very small, not doing much. But we predict that it's going to get large. Maybe it'll get even larger than the existing database. But at that point, we still have tons of headroom to grow, and we can defer making a more difficult scaling choice until later. So we do this. Events launches. That's great. This is 2014. Multiple database support in Rails is not as good as it is today, so there's a little, it's not too hard. We have to define an abstract class, blah, blah, blah. One complication is that migrations at this point do not work at all in multiple databases. We have to do a little hack. That's fine. We figure it out. So this works. We ship our feature. We ship events. Other teams see this and they think, oh, that's actually quite a nice pattern. My feature is probably also going to be very popular as well. I think it's pretty great. So now there's sort of a pattern of teams saying, well, okay, I have a new feature, let's put it on some database. So we end up with, you're starting to see how we got to the diagram at the start. We end up with a bunch of little databases, all dedicated to their own feature. And that's okay, but honestly, most of these things stay pretty small. They don't become the biggest thing in Intercom. You could think, maybe this is a premature optimization. It's probably more of a hedge. Like some of them actually do get large, and maybe we do avoid some scaling problems. But we also end up with more databases than is maybe necessary. The other thing that is a problem here is that we've added conceptual complexity to the application. If scaling was infinite and easy, we would just keep everything in one database. It would be easy to think about. You could join any table with any other table. Now we have developers are like, okay, well, where will I put my new table? Where does it make sense? So we've introduced some, cognitive overhead a little bit to buy some scaling. We're happy to do that. So that's okay. We have this pattern. We've used it. Let's skip ahead again. We've solved that problem. We're going to 2015, one more year. We have another database problem. So all these databases are growing, but under control. We know we can scale them up if we need to. And I think at this point we have hit our 4x runway. We've scaled up again on the main database, but that's okay. We applied our existing patterns. And then one day, 3 p.m. is like peak traffic time for Intercom. We're like customers all over the world, but 3 p.m. UTC is like when we have a peak. Traffic's climbing to that point and then starts to slowly taper off. And on this particular day, it did not taper off. The CPU usage of the database basically immediately shot to almost 100%. The database stalled, restarted, came back. It wasn't a long outage, but it definitely was noticeable, and the app was not working for a few minutes. So my team dug in. We looked at all sorts of things. We looked for changes. There wasn't checking, is there some customer that's doing this? Nothing really had changed from the day before that we could see. We looked for logs on the database. There was nothing obvious, no smoking gun. So we spent the day investigating this into the next day, up to 3 p.m. when it happened again, exactly the same problem the next day. And now we have a real issue. It's not just some weird outlier, one-time thing. We now have a pattern of going down at 3 p.m. every day. It's only 2 days, but we really don't want to repeat that too often. So we still can't find anything obvious. We go to AWS. They're hosting the database. Maybe they have some insight that we don't have. They can look at some like host level metrics, something like that. And we get a response back. The first thing they say is that you are running a lot of queries. Can you please maybe run fewer queries and the database will be happier and healthier? And I mean, maybe that's true, but like our application needs those queries. There's a reason we're running them, so that felt a little unhelpful. To be fair, they did flag some other things. We had some long-running transactions that might be holding things open. We had updates that would apply to thousands of rows that could clog things up. They gave us some leads, so we kind of fanned this out to our team. Our team took each of these things and investigated them, shipped some fixes. Things looked better. The next day at 3 p.m., exactly the same thing happened again. So while we were improving database performance in the abstract, we were not actually solving the real problem. So the next step was bringing in a well-regarded database consulting company who, again, gave us many, many things to try. We changed the database transaction isolation level. That seemed like it was going to be the thing. And we did something with the buffer pool. We either made it larger or smaller, I don't remember. Anyway, none of this worked. So we were sort of flailing, trying things, getting anyone to help, anyone in the company who had an idea, shipping lots of, they were great improvements, but they weren't solving the problem. While all this is going on, our team is in chaos, but our CTO finds this gem for caching database queries, thinks, okay, I'll give it a try, just goes off and ships it himself, and caches queries one at a time. So finds a high volume query running 2,000 times a second, let's cache that. Let's make sure that doesn't hit the database now. And the next day, the database was completely, absolutely happy. No outage, nothing. Well, none of the stuff we tried worked, but this did. So, I mean, I kind of made fun of AWS, but they were right. We were just running too many queries per second. We took that down, and it completely solved the problem. So yeah, my team did not solve it, but the company solved the problem. We got past this issue ourselves. So yes, the technique we applied here is caching. The best query is not running query at all. Identity cache, the gem that we use, is a read-through cache. So meaning on the left here, when you have a hit, when the data is already in the cache, you read it, you don't touch the database. Beautiful, amazing. When the data is not in the cache, it's a little more complicated. You go check if it's in the cache, it's not there. You go to the database and read the data, you write the data to the cache. Notice that this is more complicated and slower than just reading from the database. But most of the time you're getting a hit if you cache the right queries, so that's okay. When you write to the database, you need to clear the cache to make sure that you don't serve stale data. Just a little cache invalidation. This is where the problem starts, because the application down here at the bottom, like this is some process running somewhere, there's thousands of them, and it now has the responsibility to update two sources of truth or two sources of data and make sure that they are consistent, and it turns out it just absolutely cannot do that 100% reliably. And to be fair to Identity Cache, the gem we were using, they have an amazing, really clear section in the README explaining why this happens, what circumstances this happens under, saying like you really shouldn't cache things that you need to be 100% consistent. Unfortunately, we didn't read any of this because we were in the middle of a major outage. We just shipped the thing, it got us out of the hole. So we made a trade-off here. We swapped our availability issues for consistency issues, and sometimes that's fine. Serve data and it's slightly out of date, it doesn't really matter. But a bit like the other pattern we saw with adding new databases, engineers, like from the outside, they don't really know what our team is doing in intimate detail. They see the database being very unhealthy. They see us add this gem and use it, and now the database is actually amazing, working great. So you can drill that down into this gem is free performance magic that we just should use in absolutely everything, including in places where it really is bad to serve a stale read. So we had to do some work to sort of walk that back and dial down the exuberance a little bit, but when used appropriately, this is amazing. I said at the start of the talk, we serve 2 million queries from all of our databases today. We serve 10 million queries from Identity Cache. So we're still getting so much more scalability out of using this cached when we use it appropriately. So yes, we solved that problem. And we are on, again, one more year. We're marching forward year by year. This one is not as bad. It's not a major outage. It's not a customer-facing thing. But we just have seen that the CPU in the database is climbing. Queries are getting a little slower on the tail end. And we want a little less excitement this year. We want to proactively get ahead of the problem. So and I think at this point we're on one of our databases is on the largest database we can get from AWS. So we can't just get a bigger box. That would be nice, but we're not able to. So the next best thing is serving reads from a replica. So we have a second database that's just for reads. Writes are replicated there, so it has the same data, and we can send reads there. And I'm trying to tell a little chronological story here, but this is a bit out of order. We actually did have a helper, from the very start here, that we could manually route a read to the replica. But it wasn't used very often. It was mostly actually used when someone from my team would go to the product team and say, hey, this query is very slow. It's kind of not great for the database. And their idea was, OK, let's put it in the replica. The replica can handle slow queries. That's fine. But we didn't want to manually route some queries to the replicas now. We wanted to be able to send the majority of reads to replicas. And we can then scale those out. I think Amazon Aurora allows you to add 15 replicas. So we could get actually, in the best case, a lot of scalability out of serving reads from the replicas. So the question is which reads can go to the replicas. Yes. So, and the reason this made sense now is because we had been on plain MySQL, where replication lag can vary a lot depending on what's happening. It can go over a second. But we had upgraded or switched to Amazon's proprietary fork of MySQL, Aurora, which, because of the different storage engine, replication is generally almost always under 100 milliseconds. So most queries are fine now to serve from replica. We just need to make it work. And like I said, we don't want to have every controller, every piece of code decide where to send queries. We'd love to just do it automatically. So it turns out there's a gem. There's a gem that we could use for this. We found it. So the way this works is it's a new database adapter for your application. So our application used MySQL. We used the MySQL 2 gem. That's how we connect to the database. Makara sort of replaces that. Instead of being a connection to the database, it's like a little proxy that understands there are many databases. There's the writer and multiple readers, and I need to decide when a query comes in, where does it go? And like I said, you can't just send all reads to the readers. If the application writes to the writer and then tries to read that data from the reader, and it's not there, that's a bug. We can't have that happen. So it needs to be a little smarter than just writes to the writer, reads to the reader. So there's a few things it does for this. After a write in one request, all reads go to the writer. Maybe that's too much, but it guarantees that you can read all of your writes from that single request. And also, we send a cookie back from a request that did a write to say, hey, you just wrote to the database. You probably should continue to read from the writer, even if you make another request, like within 1 second. So that works quite well. It's quite easy to describe conceptually. The implementation is another matter. So like I said, it replaces the connection, Active Records connection to the database with its own thing that's like a proxy. It's a little more complicated. This is the code that does that, not too hard to understand. Then it gets a little more weird. So the adapter class is this proxy thing, and there's like a bag of SQL regexes there that match queries. There's like lots more of that, but that's maybe okay. If we dig down into the proxy, it's like dynamically defining a bunch of methods, and I don't know where the connection is yet. There's a pool. It has its own pool that has strategies, and there's like a wrapper thing. Anyway, it just keeps going and going and going. There's an enormous amount of complexity for what is conceptually a relatively simple thing to do, because it's kind of fighting with Active Record, which thinks there's one connection, and actually there's more now. If you didn't follow that, that's kind of the point. You're in my mindset now when we started using this gem. It seems to work, but like, oh my god, I can't understand what the code is doing. Oh yeah, and aside from being complicated, it's also quite using a lot of internal parts of Rails that are not part of the API, so they change between versions. The company that built this gem stopped using it, and they said, well, we'll continue maintaining it, we'll merge pull requests, we'll be good open source citizens, but you can't really well maintain something that you're not using, so it did break between Rails versions. So the idea was great, and we used it, and it worked reasonably well, but there's a lot of maintenance overhead. So yeah, when we did this, Rails did not have good support for multiple databases. Eventually it did, and we basically re-implemented the strategy, the pattern that I'm talking about here, without using this gem that was like patching Rails, and instead just using the Rails zone connections to replicas. So it got a lot easier to manage. Okay, we solved that problem. We're skipping ahead to 2019 now. So we've been going year by year and having some new database challenge. We actually now got 3 years out of this. We scaled the replicas out when we needed to. This is great. It's all paid off. Maybe we're getting out of having to constantly churn on how we run our databases. So this time it's another interesting challenge. So the largest table we have at Intercom, I think still to this day, is conversations. It's kind of the core, one of the core models of our product. Like every conversation between the business and their customer. It had grown to 25 billion rows. It was working. We could query it. There were some challenges, but the main pain point now is that we could not migrate that table. Migrating a table generally involves making a new copy, so we would have to copy those 25 billion rows into a new table and then swap them, which took many weeks. And if we had any sort of blip, any sort of failover, reset the clock, we have to start your migration again. So product teams could not work with this table effectively. We kind of got an idea. AWS started giving us a lot more attention, asking us about this database, and at some point they said something that made us think that there was not a bigger table at the time on Amazon Aurora, and you do not want to be the biggest customer of one of your vendors because you will bump into every problem. So basically, we needed to, in the immediate term, we needed to be able to migrate this table, but also we weren't sure that, okay, will it work at 50 billion rows? No idea. We can't predict that. So we need a way to split up this data. We can't keep letting this table get bigger and bigger. So our next technique is horizontal sharding. So yes, we had a big table, 25 billion rows, a big database with a table with 25 billion rows. We're now going to have multiple databases and split the data across it. So we started with 4 databases. We could have put 6.25 billion rows in each of these. That's still very large, still would have taken a long time, still have a lot of the same problems. So we actually split into a table per customer. So we have many thousands of customers. They got like striped across these 4 databases. The biggest customer had like 100, some number of 100 million rows. That's still, that's large, but it means probably within 24 hours you can migrate that schema. So it's a little more manageable. This also made schema migrations resumable. So if we did about half of these things and then we had a database failover or we restarted whatever, we could resume, right? We had a queue of migrations. And once we're done with every customer, now we have applied the schema change. We don't have to start over every time. So this solved our problem with changing the schema. Again, Rails didn't have a lot of stuff for sharding at the time. We were kind of early to a lot of the stuff. So defining the connections was not too bad. Like I said, we had a table per customer. So we wanted to route every query for that customer to their table, not like to any other customer's table. Easiest way would be to select the database for that customer at the start of the request. But now we're like, this is like a stateful thing that we need to clean up later. If we leave this here, it's a bit weird. So like the thing that we want is that every query is routed directly to the table for that particular customer. And again, like before, we held our nose and wrote a little patch. A little patch for AROL in Active Record. Not a lot of code. Needs to work correctly, so we were very careful about it. But that allowed us to have the query run on the database. Now, in order to have this patch work, we needed a little helper to say, well, which database is it? So we're kind of back to this manually sprinkling things. But it's for one table, not too bad. And we did eventually make this a little nicer. You would set the customer for the whole request, and it would happen automatically. But this was enough to get us migrated over. Yes, that let us split up that table. We don't have the largest table in Aurora anymore. We do have the largest number of tables on a database in Aurora now, though. So we've kind of traded one outlier problem for another outlier problem. I mean, it unblocked us, but we're still not ideal. But it's okay. We can add new databases. We can scale horizontally, right? We added a 5th database server when we needed to, so it gives us another way to scale up. And this actually got us all the way to 2024. So now 5 years, the gaps are getting larger. We could need to spend less time doing database projects. They are getting more elaborate and more involved, but that's okay. So now we're going to talk about the latest thing my team worked on. So what was the problem? We were on Amazon Aurora 2, which is based on the open source MySQL 5.7. The open source version was end of life. Amazon announced that their version was also end of life. So they gave us a deadline. They weren't going to like stop the database or kick us off, but they were going to start charging extended support fees that were quite expensive. I think it was 10 cents per core, but we ran many cores, so it was going to be a lot of money. So we needed to upgrade relatively quickly within that year. But also, upgrading, like we said at the start, changing a database server, restarting it, involves a little bit of customer downtime and risk. And then we now had 13 databases. So we're kind of between a rock and a hard place here. Do we zoom through these fast to save money, but annoy our customers, or do we wait and do it slowly and pay the fees? There didn't seem to be a really a satisfying way out of this on Amazon Aurora. So we looked at the options. And instead of migrating from one version of Aurora to another, we migrated to PlanetScale. Yes, the PlanetScale that is sponsoring this conference. That's a coincidence. Let's see. Yeah, so it's a bit of a bigger change than upgrading from one version to another, but PlanetScale gave us some nice things that we couldn't get from Aurora. PlanetScale is based on the open source Vitesse project, which came out of YouTube for running their MySQL infrastructure. So proven at scale, add some nice things on top for management, but effectively the setup is this. Instead of talking directly to your database, you talk to Vitesse, and Vitesse knows about your databases behind it, and it can actually allow zero downtime replacements. It can hold queries, it knows if the database is up or not, it can that all of your queries are still being issued to Vitesse, and as it swaps out the database, it'll forward all those to the new database. So instead of failing for however long, 5 minutes, 10 minutes, or like one minute or something, it can hold them. And there's still maybe some latency, but it's less of a problem for customers, right? It can also handle the sharding case, so it can manage those multiple databases and where the data lives. And from your application's point of view, it sees one database, one logical database, and the data can be scaled out and resharded. We split from 4 really large database servers to 128 much smaller servers. We can reshard whenever we want. So yes, this really let us kind of undo our own manual sharding project that did work, but involved a lot of complexity, and let us replace hosts without downtime. And that actually brings us back to the start, right? Remember, I was talking about scaling up 2 or 4x and the trade-offs involved there. We can now scale up incrementally. We can scale up one database and replace it with basically zero downtime. We can actually also scale down, which is something we would never consider before, taking downtime to save a little bit of money, but now we can do that now. So yes, we came all the way around to now solving our original problem of database downtime. So that brings us up to 2025. We are here now. I'm hoping the gaps are getting longer. I'm hoping for another 5 years, hopefully. We'll see. Maybe I'll give an updated talk at some point when we hit another scaling bottleneck. But yeah, that's the quick tour of scaling techniques we've used at Intercom to scale to 2 million queries per second. Thank you.